Hello, I'm Ali. I'm the PhD student of the University of the Sao Paulo. I would like what I did in the master degree here as a presentation. The title of my presentation is about Lumper differential model for the icing prediction in heated P2 tube. So I divided my works in 6 parts: motivation and objectives, background of the work, problem formulation, solution methodology, result and discussion, and the final conclusion and the way forward. As a last presentation, I have a new motivation to say, so I will pass very rapidly about the motivation. Ice formation is one of the fundamental problems of the aviation, because the icing may occur on wing control surface tube. On the other hand, the theoretical analysis involves the proposition of the lump differential model for the heat conduction. So what is happening? In this picture, we can see what maybe happened, the ice formation. In the other part of the aviation can be happen, one like that the blades, the entrance of the motor, the antenna in the front of the glass of cockpit, boarding edge, a lot of sensors like the P2 tube. And the basic effect of ice formation on the aviation is the reducing lift and increasing the drag force. So I want to show you a small video about the ice formation effect of the pressure field along of the air foil. Because the ice formation and ice accretion change of the geometry of the airfoil. And with the change in the geometry of the airfoil, the basic design of it will be changed, and maybe change the velocity and pressure and make some problem for the aviation, like that's here. Here, it's change the separation point 2. But for the problem formulation, I will explain a little about the ice formation in the airfoil, because we have a lot of the paper and the works for the airfoil, and we are using this method for the implement to the heated tube, heated tube. The second part is the conjugated heat transfer analysis of the heated P2 tube. And the last part is the conjugated heat transfer analysis of heated tube with ice formation. So one of the most important parameter for the ice formation is the beta, the local collection efficiency that I show here, as we know the relation of the beta. And this is the energy balance in the surface, in the airfoil. And the second one is the mass balance in the surface. In the another resistance can the mass of ice, mass of the fluid, and another part can be evaporate, solid, liquid, and ice acceleration. In this part we have some equation about the ice thickness and relation of the beta, and accumulation of the parameter of accumulation and acceleration, and the beta in the stagnation point. And this is the problem formulation for the radially average temperature distribution. That's in the function of the time and x. And this equation is the first equation we make to solve the heat transfer coefficient, but without any ice formation. And this part is some a result of this equation, the comparison of the experimental and surface temperature at the steady state for validation of the thermal model is some paper from one of my colleagues, Roberto Souza. And this is some comparison for the two of the simplified model for the validation thermal and experimental cousable. And then another paper of the José Roberto. And we want to start talking about the ice formation and the PT tube. So we can see this part, what's maybe happen when some streamline the crossing of the airfoil. There is a lot of the droplet of the water can be impacted in the airfoil and the PT tube too. And there is a relation for the velocity and local collection efficiency for one PT tube, and the relation of the relation movement of the one droplet and the velocity of the ambient. And in this part, we modified this equation with a new boundary layer. In this boundary layer, we added a new part for the latent heat transfer, because we have heat and mass transfer in the ice formation, and some new relation for the convective heat transfer coefficient. That is the relation between the two kind of the ice can be happen, the ice thickness and the water height. And as we know, can be happen two kind of the ice in the aviation. Is the like the ice glaze and rime ice. And I want to show you a small video. It is one of the first training for the pilot to understanding the relation between the ice, two kind of ice, and how to control aviation in this situation. It's a movie about the this first kind of the ice is the rime ice. And this ice we are using for the E2 is the glaze ice or clear ice. But the solution methodology of the work, the proposed combined model together with identifying parameter and properties described range have been implemented, symbolic and numerical platform as resolved by the Mathematica. Mathematica is the one program on the Wolfram and solved numerically by the method of line available in a subroutine for solving differential equation we called NDSolve. The NDSolve handles about nonlinear differential equation as a simultaneous equation with a differential with automatic control system, absolute and relation error. This function provided the solution and the object code approximating behavior of the independent variable continuous function. But the numerical results were also verified against the error control solution with the unit method is the unified integral transform. It's made by the Professor Sphere and Professor Kota for the with implementing automatic hybrid numeric analytical solution. And in this part, we want to explain a little about the result and discussion. We simulate in the three conditions our equation. The first one is the condition of the flight Air Force Skywalk, the Brazilian military. Second one, the flight of the accident Air France. And the third one is the situation and condition of kilometer-wide tunnel of the copy. That here. So this is a proposed model. We know it very well. And this is the first simulation for the prediction of theoretical temperature along of the PT tube with the ice formation in the in this kind of the Mach and this altitude. That's a predict, and this showing the behavior of the temperature after starting the icing And this is a 3D model of that in this situation, temperature. In this one, we comparison of the prediction theoretical temperature along of the P2 tube before and after starting icing test. In this part, the green line is showing the temperature before starting the icing in the our model, and after is starting by the time the our model with the icing. It is showing the decreasing of the temperature. And this one is showing transient behavior of the temperature in stagnation region by the time for the tested flying of the A4. We can see how about the 8,050 seconds the freezing started. And the second part of the second condition of our presentation is about the flight AF 447 rear to the Paris. In this picture, we can see the position of the P2 tube on the Airbus. And this is some movie trying to simulate what's happened for this aviation when he arrived to the cloud with the droplet. The icing was started. That place. He sent some signal to the radar, and we can know after entering some aviation in the cloud, because of the new part of ice formation, the temperature is decreasing, and we try to show it. This photo is showing us the location of the Airbus, that is located the P2 tube. In this picture, we try to in this slide we try to find a comparison of the theoretical prediction temperature along the P2 tube and the situation of the accident. It's showing the time, the true time of the testing with the icing, and the second one is showing the transient behavior of the temperature by the time. But when I was researching about the P2 tube, we understanding the conical section of the P2 tube, because in this part there is no any thermal resistant. So it's very effective to starting ice formation and ice accretion in the P2 tube. So we modificate a new convecting heat transfer coefficient with ice thickness and water height in this part, and we solve again the equation to find the result. We change this part of the equation and put this part in the equation to it's for the transient behavior of the P2 tube too. And it was very interesting because the time of the ice formation is reduced after put this modification on the P2 tube, and about 1,000 seconds the time of icing is reducing. So, and the third part, we have the test condition of climate vine tunnel of the copy. That tunnel everybody know. The last day we saw it, and the precision of the theoretical prediction at the tunnel with the situation of the tunnel of the wine, and the temperature for the start freezing. And the temperature is a function, is a transient behavior of the temperature by the time here. In the another condition of the climate vine tunnel with different liquid water content and different temperature. And the transient behavior of the temperature by the time here with the new condition of the tunnel. So in this work, we proposed a conjugated heat transferring model for thermal analysis of an aeronautical P2 tube combined with a simplified formulation of the icing formation, but there is, although the main objective of the research is development of the model for the analyze, but for the part of the anti-icing system, it's showing a need to be optimized because including modifying geometry of the P2 tube, because as we saw, the conical part of the P2 tube is very effective to starting ice formation because this place isn't any thermal resistant, and it can be some work for the future. Just that.